Welcome to our discussion of mass spectrometry, which is module 1.1.3. So what I want to do is give you a bit of a description about what a mass spectrometer looks like and how it works, because in the earlier discussion I mentioned things like isotopes and mass numbers and different relative abundances, and I made a very vague statement that we know these relative abundances from a mass spectrometer, but I didn't really tell you exactly how a mass spectrometer works. And so what I'm going to do now is show you a schematic of a mass spectrometer so you can see one. Okay, and so over here is our schematic for a mass spectrometer, which we will call MS for short. And the way a mass spectrometer works is first you inject a sample right here. The sample typically is in the gas phase, could be a liquid, could be a solid, but usually a gas. And it goes in through here, and then it enters this section where there's an electron beam source. And the electron beam you can basically think of as a gun of electrons, just poof, 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 shoots electrons at this thing and causes the sample to get ionized. Okay, it's going to have an excess of negative charges. So now these particles have charges associated with them. They pass through these plates, very similar to what you saw in the oil drop experiment and in Thomson's experiment, which causes them to accelerate. And then they enter this curved part and they bend. And they're going to bend a certain amount depending on how heavy they are. Okay, so the mass will affect how much it curves. Okay, and so some of the heavier ones might deflect a little bit less, and the lighter ones might deflect a little bit more. And they bounce off at different angles, and eventually they hit a detector over here. And the detector records the data for how many ions or how many particles got trapped at a certain point in time. And the output is what is called a mass spectrum. And an example of a mass spectrum is here on the right. Okay, and so my x-axis is my mass to charge ratio, m over z, and my y-axis is a relative abundance, which we were calling F before, for fractional abundance. And what happens is all of the different isotopes get separated by their mass to charge ratio. Because they have different masses, they're going to bend or get deflected different amounts, and so I can separate them this way. And so this happens to be for element Zr, zirconium, and you can see that there are 1, 2, 3, 4, 5 different isotopes for zirconium. There's zirconium 90, 91, 92, 94, and 96. And each of them has a different abundance, which is related to how many ions got sort of detected at the end. So the most abundant one, for example, zirconium 90, right, about half, a little bit more than half of all of the zirconium is zirconium 90. And the least abundant one looks like it's zirconium 96, probably less than 10%, maybe 5% or so of it is that. And so this is how scientists determine the relative abundances of all of these different isotopes using a mass spectrometer. And here's a table that illustrates just some typical elements and what their ratios are. Again, this is not something you have to memorize, but just to kind of show you how to interpret the data and how to do something with it. Okay, and so on the left here, I'm showing you some different elements that you might come across, right? Hydrogen, carbon, nitrogen, oxygen, chlorine, and bromine, and the common isotopes. So for most of these things, you'll see 2 or 3 different isotopes. And again, for most elements, you'll notice that there's typically one isotope that is very, very, very abundant, right? Almost 100%. So for example, for hydrogen, 99.985% of the hydrogen on Earth is what's called protium, which is just regular hydrogen with 1 proton and no electrons whatsoever. Or for carbon, something like 98.9% of it is carbon-12. But there are some exceptions. Okay, so if you look down here on the bottom, for chlorine and for bromine, chlorine does have a dominant isotope, right, chlorine-35, which is about 75.77% of the chlorine on Earth, but there's still a significant amount, 24.23% of chlorine-37. So the ratio here is about 3 to 1, as opposed to like 99.999% and very little of something else, right? There's still a good amount of this other isotope. The other famous exception is bromine. So bromine exists in two main isotopes, bromine 79 and bromine 81. And if you look in the periodic table, the molar mass or atomic weight for bromine is listed as 79.9. And so you might think that that's because the most common isotope is bromine 80, but that's actually false. There's very little bromine 80, if any, on Earth. The vast majority of the bromine on Earth is either bromine 79 or bromine 81. But what happens is, just by sheer chance, about half of the bromine on Earth is bromine 79, and about half of the bromine on Earth is bromine 81. And because they're present in about equal amounts, they average to about 80. Okay, so you can see here, 50.69% of the bromine is bromine 79, 49.31% is bromine 81. So that accounts for my 1-to-1 ratio. And this concludes our section on mass spectrometry and isotopes.